When astronomers first spotted 3I Atlas racing through our solar system in 2025, the scientific community erupted with excitement. Here was our third confirmed interstellar visitor, an ancient wanderer that had travelled billions of years through the cosmic void to reach us. The headlines screamed about alien chemistry and exotic ices from another star system. Social media exploded with speculation about what secrets this mysterious traveller might reveal about distant worlds we could never hope to visit. But while everyone was looking up at the sky, captivated by this exotic visitor from beyond, something far stranger was hiding in plain sight much closer to home. An object that's been orbiting quietly in our own solar system for billions of years, patiently waiting for us to notice just how extraordinary it truly is. This isn't some flashy newcomer from the depths of space. This is a permanent resident that makes 3I Atlas look downright ordinary by comparison. Its name is 2060 Chiron, and what we've discovered about this enigmatic object over the past few years has completely shattered our understanding of how small bodies work in space. While 3I Atlas may have grabbed the headlines with its interstellar origins, Chiron is quietly rewriting the textbooks on planetary physics right here in our cosmic backyard. You see, Chiron isn't just unusual, it's impossible, at least according to everything we thought we knew about comets, asteroids, and the fundamental laws that govern how matter behaves in space. This object is surrounded by rings that exist in locations where basic physics says they should have collapsed into moons millions of years ago. Yet there they are, organised and evolving before our very eyes, defying every model we've built to explain ring systems. But the rings are just the beginning. Chiron is also venting primordial gases like methane and propane, behaving like some ancient time capsule slowly opening to reveal secrets from the early solar system. And perhaps most remarkably, it's doing all of this in real time, changing on scales we can actually observe and measure during a human lifetime. If you're fascinated by cosmic mysteries that challenge our fundamental understanding of physics, you'll want to stick around for this entire journey. Hit that subscribe button and turn on notifications, because what we're about to explore will change how you think about our solar system forever. And make sure to leave a comment telling me where you're watching from and what time it is in your corner of the world, because this story connects observers across the globe who are all witnessing the same impossible phenomenon. Now, before we dive into the mind-bending details of what makes Chiron so extraordinary, we need to understand why everyone was so excited about 3I Atlas in the first place. Interstellar visitors are incredibly rare. In all of human history, we've only confirmed 3 objects that came from beyond our solar system and passed through our cosmic neighbourhood. The first was Oumuamua in 2017, that strange cigar-shaped object that sparked debates about whether it might be artificial. The second was Comet 2I Borisov in 2019, which behaved like a relatively normal comet and didn't cause nearly as much controversy. Then came 3I Atlas in 2025, the latest visitor and newest mystery. When it was first detected by the Atlas Survey Telescope in Chile on July 1st, it appeared to be just another faint dot moving against the background stars. But as astronomers calculated its trajectory, they realised something remarkable. This wasn't an asteroid bound to our Sun. The path was hyperbolic, meaning it came from somewhere else and was just passing through. The excitement was understandable. Here was a chunk of ice and rock that had formed around a completely different star, in a completely different stellar environment, carrying chemical signatures from a distant corner of the galaxy. By studying this object, scientists could essentially get a free sample delivery from another solar system without having to send a probe on a 1,000-year journey to another star. As 3I Atlas got closer to the Sun and began warming up, it started showing the classic signs of comet activity. A fuzzy coma of gas and dust formed around its nucleus. It developed a tail. Telescopes around the world turned their attention to this ancient traveller, eager to decode the secrets it carried from its birthplace among alien suns. The James Webb Space Telescope detected water vapour, carbon dioxide, and other materials exactly what you'd expect from a comet. Radio observations picked up hydroxyl emissions as water molecules broke apart under solar radiation. Every measurement confirmed that 3I Atlas was behaving like a natural comet, albeit one with some unusual characteristics due to its exotic origin. But here's what's remarkable. While 3I Atlas was putting on this spectacular show as it approached the Sun, generating headlines and capturing imaginations worldwide, Chiron was quietly doing something that should have been making front-page news everywhere. It was hosting multiple organized ring systems around a nucleus barely 200 kilometers across. Not one ring, but several distinct narrow bands of material orbiting this tiny object like miniature versions of Saturn's famous rings. Think about that for a moment. Saturn's rings exist because Saturn is a massive planet with enormous gravitational influence capable of capturing and organizing debris into stable structures. Saturn's mass is so great that it can maintain ring systems spanning hundreds of thousands of kilometers. But Chiron is roughly the size of a large asteroid, with gravitational influence so weak that ring particles should either fall back to the surface or drift away into space within a relatively short time. Yet somehow, impossibly, Chiron's rings persist. Not only do they exist, but they're confined into narrow bands with sharp edges, organized in ways that require mechanisms we don't fully understand. Some of these rings sit outside what's called the Roche limit, the boundary where gravitational forces should cause ring material to clump together and form moons. According to our best models of orbital mechanics, material at those distances should have aggregated into satellites millions of years ago. The discovery of these rings came through one of astronomy's most elegant techniques called stellar occultation. When Chiron passes in front of a distant star, astronomers can watch how the starlight changes to map out exactly what's surrounding the object. It's like reading Braille written in flickering starlight, and what it revealed about Chiron was absolutely extraordinary. The first hints came in 2011 when observers noticed that starlight didn't just blink out once as Chiron passed in front of it. Instead, it flickered multiple times in symmetric patterns, suggesting some kind of organized structure around the object. At the time, most researchers thought they were seeing temporary debris clouds, or jets of material being vented from the surface. But as more occultations were observed in 2022 and 2023, the pattern became undeniable. Multiple independent observation campaigns confirmed the existence of at least 3 distinct narrow rings at specific distances from Chiron's center. These weren't random clouds of debris, they were genuine ring systems with sharp boundaries and organized structure. What makes this even more extraordinary is that Chiron isn't a dead, frozen rock. It's geologically active, constantly venting gas and dust into space like a comet, but at distances from the Sun where comets aren't supposed to be active. At 18 astronomical units from the Sun, roughly between the orbits of Saturn and Uranus, temperatures are so cold that most comet activity should be impossible. Yet Chiron is producing significant amounts of methane, carbon dioxide and other gases. The James Webb Space Telescope detected these emissions and found something fascinating. The methane wasn't just sitting passively on the surface, it was actively fluorescing under sunlight in a way that indicated ongoing outgassing from Chiron's interior. This activity is likely driven by something called the amorphous to crystalline ice phase transition. Deep inside Chiron, ancient water ice that formed in a disordered state billions of years ago is slowly crystallizing and releasing trapped gases in the process. When this happens, it's like a pressure cooker releasing steam. The sudden venting of material can launch debris into orbit, potentially feeding and maintaining the ring system through periodic outbursts. Between March and September 2021, Chiron experienced exactly this kind of event. Its brightness increased dramatically, indicating a major release of material. If that material was ejected with the right velocity and in the right direction, it could have gone into orbit around Chiron, adding fresh particles to the existing rings and helping to explain how these impossible structures persist. This is what makes Chiron so scientifically valuable. We're not just looking at a static ring system left over from some ancient collision, we're watching a dynamic, evolving system that's being actively maintained by ongoing geological processes. It's a natural laboratory where we can observe ring formation and evolution happening in real time, on timescales short enough for human scientists to track and study. The implications go far beyond just understanding one unusual object. If Chiron can maintain rings through active processes, how many other small bodies in our solar system might be doing the same thing? How many asteroids and comets might be surrounded by structures we've never thought to look for because our models told us they couldn't exist? This challenges our fundamental understanding of how ring systems work. For decades, astronomers have studied the magnificent rings of Saturn, Jupiter, Uranus, and Neptune, building theories about how such structures form and evolve. But all of those examples involve massive planets with enormous gravitational fields. Chiron is showing us that the physics of ring systems might be far more complex and nuanced than we ever imagined. The discovery of rings around small bodies like Chiron opens up entirely new questions about solar system evolution. During the chaotic early days when planets were still forming and objects were constantly migrating and colliding, how many small bodies went through a ringed phase? Could ring formation be a common stage in the evolution of asteroids and comets as they're heated and activated by their journey through the solar system? These are the kinds of questions that make Chiron far more than just an interesting oddball. This object is forcing us to rewrite our understanding of planetary physics, to expand our models of how matter organizes itself in space, and to accept that the universe is capable of surprises we never anticipated. While astronomers around the world were tracking 3I Atlas through its spectacular journey past the Sun, something equally remarkable was happening in laboratories here on Earth. Scientists were making discoveries that would fundamentally change our understanding of how matter behaves under extreme conditions. But we'll get to that connection in a moment, because first we need to dive deeper into just how impossible Chiron's ring system truly is. You see, when we talk about the Roche limit, we're dealing with one of the most fundamental concepts in celestial mechanics. This boundary, calculated by French astronomer Édouard Roche in the 1850s, represents the distance from a celestial body where tidal forces become stronger than the gravitational forces holding an object together. Think of it this way. If you're a small moon orbiting too close to a planet, the planet's gravity pulls harder on your near side than your far side. Eventually, those tidal forces literally tear you apart, spreading your debris into a ring. For Chiron, with its radius of roughly 110 kilometers, the Roche limit should extend only about 200 to 300 kilometers from its center. Yet one of its confirmed rings sits at 438 kilometers out, well beyond this critical boundary. An even more mysterious diffuse feature extends all the way out to 1,280 kilometers. According to everything we know about orbital mechanics, material at these distances should have clumped together into proper moons millions of years ago. But here's where it gets even stranger. Recent computer simulations have revealed that Chiron's irregular potato-shaped form creates a gravitational environment unlike anything we've studied before. The object isn't a nice uniform sphere, it's what astronomers call triaxial, meaning it's elongated and lumpy. This creates regions where gravity is stronger and weaker, in ways that change as Chiron rotates. These gravitational variations might be acting like invisible shepherds, confining ring particles into narrow bands through something called spin-orbit resonances. These are special orbital configurations where a particle's orbital period matches Chiron's rotation period in simple mathematical ratios. It's possible that Chiron is essentially herding its own rings through these resonance effects, creating the first known example of a self-shepherding ring system. The observational evidence keeps piling up in ways that challenge our assumptions. Between 2011 and 2023, multiple stellar occultation campaigns have captured snapshots of Chiron's environment at different points in time. When researchers compare these observations, they see differences. Not subtle, maybe it's just noise differences, but real, measurable changes in the structure and density of the material surrounding Chiron. Some features that appeared prominent in 2023 observations weren't as visible in earlier data. The rings seem to be evolving, reorganizing, responding to forces we haven't fully identified yet. This suggests we're not looking at ancient static structures, but at a dynamic system that's actively changing on timescales we can observe. Think about what this means for our understanding of how planetary systems form. Traditional models assume that ring formation is a slow, gradual process taking millions of years. Small particles stick together through countless collisions until larger and larger objects form. Eventually, if conditions are right, you get moons. But what if that process can be accelerated under certain conditions? What if we're watching the very early stages of satellite formation compressed into decades instead of eons? This is where the story gets even more fascinating because Chiron might not be unique. As astronomers have started looking more carefully at other small bodies in our solar system, they've found that ring systems on asteroids and comets might be far more common than anyone suspected. Chiron, another centaur discovered in 1997, shocked the scientific community in 2013 when stellar occultations revealed it has two narrow, dense rings. Just like that, The idea of ring systems on small bodies went from theoretical curiosity to observed reality. Then came Haumea, a dwarf planet in the Kuiper belt that spins so fast it stretched into an elongated shape. In 2017, astronomers discovered it too has a ring system. More recently, Quaoar, another Kuiper belt object, was found to host a ring located outside its Roche limit. Just like Chiron. The pattern is becoming clear. Small bodies with ring systems aren't just possible, they're apparently common once you start looking for them systematically. But here's what makes this discovery so profound. If ring systems are a normal phase in small body evolution, then we've been missing a huge piece of the puzzle about how our solar system formed and evolved. During the chaotic early period when planets were still accreting and objects were constantly being kicked around by gravitational interactions, the solar system might have been filled with ringed bodies at various stages of development. Some would have been destroyed in collisions, their rings merging with other structures or dispersing into space. Others might have been ejected from the solar system entirely, carrying their rings with them into interstellar space. And perhaps most intriguingly, some of these ringed objects might have delivered water and organic compounds to the inner solar system, seeding the young Earth with the chemical ingredients necessary for life. This fundamentally changes how we think about the distribution of materials throughout the galaxy. If objects like Chiron can maintain active ring systems while migrating through different regions of a planetary system, then they become vehicles for transporting and redistributing matter across vast distances. The building blocks of life might not just form locally around each star, but could be constantly exchanged between stellar systems through these wandering, ringed ambassadors. What's particularly striking is how Chiron's behavior connects to cutting-edge research happening in completely different fields. While astronomers struggle to understand how ring particles organize themselves around irregular bodies, materials scientists are discovering that matter can self-organize in ways we never expected under the right conditions. Recent breakthroughs in quantum materials research have shown that electrons in certain compounds can form organized structures at room temperature, defying classical physics predictions about when quantum effects should disappear. These discoveries reveal that the boundary between quantum and classical behavior is far more complex than textbooks suggest. Just as Chiron reveals that the boundary between where rings can and cannot exist is more nuanced than our models predicted. The parallel is striking. In both cases, we're seeing matter organize itself in ways that seem to violate fundamental rules, suggesting that our understanding of how complex systems behave is still incomplete. Nature appears to have mechanisms for creating and maintaining organization that we're only beginning to discover. This is what makes studying objects like Chiron so valuable. They're not just astronomical curiosities, they're windows into physical processes that operate across scales, from the quantum realm of electrons in crystals to the cosmic scale of particles orbiting in space. By understanding how Chiron maintains its impossible rings, we might gain insights that apply to entirely different fields of science. The question now is whether we're witnessing something truly unprecedented, or whether we've simply been looking in the wrong places for the wrong things. How many other objects in our solar system are hosting dynamic evolving structures that we've overlooked because our theories told us they couldn't exist? How many asteroids, comets, and small moons might be surrounded by rings, clouds, or other organized features that we've never thought to search for? The technology to answer these questions is finally within our reach. Automated survey telescopes can monitor thousands of objects simultaneously, watching for the telltale signs of occultations that reveal hidden structures. Advanced computer models can simulate the complex gravitational environments around irregular bodies, predicting where stable orbits might exist despite classical theory saying they shouldn't. Perhaps most importantly, we're developing the conceptual frameworks needed to think about these problems in new ways. The discovery of Chiron's rings isn't just adding another data point to our catalogue of solar system objects. It's forcing us to question fundamental assumptions about how matter behaves in space, how structures form and persist, and what's possible in the vast laboratory of the cosmos. As we continue to monitor Chiron over the coming years and decades, we'll be watching a planetary physics experiment unfold in real time. Will the rings continue to evolve? Will they eventually coalesce into moonlets? Will new outbursts inject fresh material and reshape the entire system? We don't know, but we have the tools to find out. And this is where our story takes a truly remarkable turn. Because while we've been focused on Chiron's impossible rings and real-time evolution, something equally extraordinary has been unfolding in laboratories around the world that connects to this cosmic mystery in ways nobody anticipated. In 2025, researchers achieved what many thought was impossible. They successfully controlled quantum geometric effects in materials at room temperature. Now, you might be wondering what quantum geometry has to do with a comet orbiting between Saturn and Uranus, but the connection is more profound than you'd expect. Quantum geometry describes how electrons organize themselves in materials, creating structures and behaviors that classical physics says shouldn't exist. For decades, scientists believed these effects could only be observed under extreme conditions. Ultra-low temperatures, powerful magnetic fields, precisely controlled environments that cost millions of dollars to maintain. But the breakthrough came with a compound called terbium manganese tin, where researchers discovered they could tune quantum effects using simple magnetic fields at everyday temperatures. Electrons were forming organized patterns, creating responses that could be switched on and off, demonstrating that matter has hidden mechanisms for self-organization that we're only beginning to understand. The parallel to Chiron is striking. Just as electrons are organizing themselves in ways that seem to violate classical rules, Chiron's ring particles are maintaining structures where classical orbital mechanics says they should collapse. Both systems are showing us that the universe has tricks up its sleeve, mechanisms for creating and preserving organization that our simplified models missed entirely. This isn't just an academic curiosity. These discoveries are revealing that the boundary between order and chaos, between what's possible and what's not, is far more complex than we realized. Nature appears to have multiple pathways for building structure from apparent randomness, whether we're talking about electrons in crystals or dust grains around distant comets. But the implications go even deeper. Recent advances in artificial intelligence have shown us that the same principles governing natural organization can be harnessed to create entirely new forms of complexity. In 2024, AI systems successfully evolved proteins that never existed in nature, compressing millions of years of evolutionary development into computational processes that ran for just weeks. These artificially evolved proteins weren't designed in the traditional sense. They emerged through algorithmic processes that mimicked natural selection, testing countless variations until functional structures appeared. The result was ESMGFP, a fluorescent protein that glows green under ultraviolet light, sharing only 58% genetic similarity with any natural protein, yet performing its biological function perfectly. Think about what this means. We now have the ability to guide evolution, to accelerate the processes that create complexity in nature, and this capability is expanding rapidly. If we can evolve proteins computationally, might we someday simulate entire planetary systems, testing different conditions to understand how ring structures form and persist around objects like Chiron? The computational challenge would be enormous, simulating millions of interacting particles over thousands of orbital periods, tracking collisions and gravitational effects with high precision. But the principle is the same as protein evolution. Use computation to explore possibility space far faster than nature does alone, then extract insights about which configurations are stable and which are transient. This convergence of discoveries across multiple fields suggests we're entering a new phase of scientific understanding. For centuries, we've been observers, watching nature do its thing and trying to decode the rules. Now we're becoming participants, learning to collaborate with the processes that create complexity, whether in space, in materials, or in biological systems. And this brings us back to one of the most unsettling questions raised by modern physics. If we can simulate evolution, if we can model quantum systems, if we can predict how matter organizes itself under different conditions, are we approaching the point where the distinction between natural and artificial becomes meaningless? Recent mathematical proof suggests the answer is more complex than we might expect. In 2025, physicists published a demonstration that the universe cannot be purely computational, cannot be reduced to a simulation running on some cosmic computer. Their argument relies on fundamental limits in mathematics itself. The same principles that show certain mathematical truths can never be proven within any formal system. This has profound implications for how we think about anomalies like Chiron. If reality contains non-algorithmic elements, aspects that can't be captured by pure computation, then objects like Chiron aren't glitches in some cosmic program. They're features of a genuinely complex universe that will always have the capacity to surprise us. Consider what we've learned about our own planet recently. While astronomers have been studying distant objects, oceanographers made a startling discovery much closer to home. The deep Arctic Ocean is warming rapidly, not from surface heating as everyone expected, but from below. Deep water currents are carrying heat into the abyssal layers of the Arctic basin, creating a hidden thermal engine that could fundamentally alter global climate patterns. This deep warming was invisible to most observations. You could stand on Arctic ice and never know that kilometers below your feet, the ocean's thermal structure was shifting in ways that could reshape weather patterns across the globe. It's a reminder that the most important processes often happen in the places we can't easily see. The same principle applies to Chiron. On the surface, it looks like a relatively simple object, a small comet tumbling through space. But beneath that surface, multiple processes are at work. Ice is crystallizing, releasing trapped gases. Internal heat sources are driving out gassing events. Gravitational resonances are organizing ring particles into stable configurations despite classical theory saying they should disperse. What makes this particularly fascinating is the timescale. Most planetary processes take millions or billions of years to unfold. Mountain ranges rise over geological epochs. Continents drift across spans of time that dwarf human civilization. But Chiron is changing on scales we can observe directly. Ring structures evolving over years and decades. Outgassing events happening in real time. A planetary physics experiment unfolding at human speeds. This accessibility is unprecedented in planetary science. Usually we study the end results of ancient processes, trying to reconstruct what happened billions of years ago from evidence preserved in rocks and craters. With Chiron, we can watch the process itself, observing how ring systems form and evolve, how matter organizes itself around small bodies, how geological activity on tiny worlds can create and maintain complex structures. The observational campaigns required to study Chiron represent international cooperation at its finest. Teams across multiple continents coordinate their efforts, positioning telescopes along predicted shadow paths, sharing data in real time, building collaborative models that no single institution could create alone. When Chiron passes in front of a distant star, observers from Chile to Spain to South Africa all contribute pieces of the puzzle. These occultation events last only seconds, but they require months of preparation. Calculating precise positions, coordinating observations across time zones, ensuring that weather and equipment don't interfere with the brief moment when crucial data becomes available. It's astronomy at its most challenging and most rewarding, and the data keeps revealing new surprises. The most recent observations suggest that Chiron's ring system isn't static. Material appears to be moving, reorganizing, responding to forces we haven't fully identified. Some features visible in 2023 weren't present in earlier observations. Others have changed position or intensity. This dynamic behavior raises fascinating questions about the mechanisms driving ring evolution. Are we seeing the effects of Chiron's chaotic rotation? Gravitational perturbations from unseen moonlets? Periodic outgassing events that inject fresh material and reshape existing structures? The answer probably involves all of these factors working together in ways we're still trying to understand. What's becoming clear is that Chiron represents a new category of object entirely. It's not quite a comet, not quite an asteroid, not quite a small planet. It's something hybrid, something that blurs the boundaries between classifications we thought were fundamental, and in blurring those boundaries, it's teaching us that nature doesn't respect the neat categories we try to impose on it. This lesson extends far beyond astronomy. In quantum materials research, scientists are discovering substances that exist in multiple states simultaneously, defying classical categories. In biology, AI-evolved proteins challenge our understanding of what's natural versus artificial. In oceanography, deep thermal engines operate according to principles we're only beginning to comprehend. The pattern is clear. Across every field of science, researchers are encountering systems that resist simple classification, objects and phenomena that exist at the boundaries between different domains, challenging us to think more flexibly about how the universe works. Chiron is part of this larger trend toward recognizing complexity and embracing the unexpected. Perhaps most importantly, Chiron is teaching us about the nature of scientific discovery itself. Progress doesn't come from confirming what we already believe. It comes from encountering things that don't fit our models, that force us to expand our understanding, that humble us with their complexity and beauty. For decades, Planetary scientists built theories about ring systems based on the giant planets. Saturn, Jupiter, Uranus, and Neptune provided the templates for understanding how rings form, evolve, and interact with their environments. Those theories worked well for massive worlds with enormous gravitational fields and complex satellite systems. But Chiron is showing us that ring physics is far richer than those examples suggested. Small bodies can maintain organized structures through mechanisms we never considered. Irregular gravity fields can act as shepherds. Active geology can feed ring systems over long periods. The universe has more ways of building complexity than we imagined. And this is just the beginning. As survey telescopes become more sophisticated and occultation predictions become more accurate, we'll undoubtedly discover more small bodies with unexpected structures. Ring systems, dust clouds, satellite swarms, features we haven't even thought to look for because our theories told us they couldn't exist. Each discovery will refine our understanding, force us to revise our models, challenge us to think more creatively about what's possible in the vast laboratory of space. Chiron won't be the last impossible object we encounter. It's the first of many that will reshape our understanding of how matter behaves in the cosmos. The story is far from over. In fact, we're just reaching the point where the real mysteries begin to unfold. Because what we've discovered about Chiron so far is leading us toward questions that could revolutionize our understanding of planetary formation itself. Questions about how common these processes are, how they connect to the larger story of solar system evolution, and what they might tell us about the potential for life in environments we never thought to consider. But those revelations require us to dive even deeper into the physics of what makes Chiron possible, and to confront some uncomfortable truths about the limits of our current understanding. Because the more we learn about this impossible object, the more we realize how much we still don't know about the universe we call home. Home. The deeper we dig into Chiron's mysteries, the more we realize we're confronting something that challenges the very foundations of planetary physics. And here's where the story takes a turn that nobody saw coming. Because while astronomers have been focused on understanding how Chiron's rings could possibly exist, they've uncovered evidence that this object might be operating multiple engines simultaneously. Not just one mechanism driving its impossible behavior, but several different processes working together in ways we're still trying to untangle. Think about what we know so far. Chiron is venting methane and propane at distances from the Sun, where solar heating alone shouldn't be able to drive that kind of activity. It's maintaining ring structures, where classical physics says they should collapse. It's experiencing brightness outbursts that inject fresh material into its system. And it's doing all of this while tumbling chaotically through space with a rotation that's anything but stable. The leading explanation for Chiron's activity centers on something called the amorphous to crystalline ice phase transition. Deep inside this object, ancient water ice that formed billions of years ago in a disordered state is slowly crystallizing. When that happens, it releases energy and trapped gases in explosive bursts. It's like a geological time bomb that's been ticking for eons, finally going off now that Chiron has migrated close enough to the Sun for temperatures to trigger the transition. But here's what's making researchers uncomfortable. That mechanism alone might not be sufficient to explain everything we're observing. The outgassing patterns are too complex, too varied, too precisely timed to be driven by a single process. Different volatiles are being released from different regions of Chiron's surface. The ring structures are too organized, too stable for random outbursts to maintain them effectively. Some scientists are starting to suspect that Chiron has multiple engines running simultaneously. Cryovolcanism, where internal heat drives eruptions of icy material through cracks in the surface. Mechanical fracturing, where Chiron's chaotic rotation creates stress patterns that open vents at predictable intervals. Even impact-driven processes, where small meteoroids hit the surface and kick up debris that joins the ring system. The idea of a multi-engine system would explain the complexity we're seeing. Why methane and carbon dioxide vent from different locations. Why the ring structure changes over time but remains organized. Why outbursts happen with timing that seems too precise to be random. If several different mechanisms are operating together, feeding off each other, creating feedback loops that amplify and regulate the entire system. But proving this hypothesis requires observations we don't have yet. We need higher resolution images of Chiron's surface to map where different gases are being released. We need long-term monitoring to track how outgassing correlates with ring changes. We need models sophisticated enough to simulate multiple interacting processes over thousands of orbital periods. The computational challenge is staggering. Modelling just the gravitational dynamics of millions of ring particles is hard enough. Adding thermal evolution, chemical processes, surface geology, and chaotic rotation pushes the problem into regimes where even our most powerful supercomputers struggle. But that's exactly what we need to understand how Chiron works. Meanwhile, the observations keep piling up in ways that deepen the mystery rather than solving it. The most recent stellar occultation data suggests that Chiron's outer ring, the one sitting well beyond the Roche limit, might actually be expanding. Material that should have clumped into moons appears to be spreading outward instead, defying gravitational logic in ways that make theorists genuinely nervous. There's also growing evidence that Chiron's ring system isn't symmetric. Different chords through the occultation shadow show different structures, suggesting that material might be concentrated in arcs rather than complete rings. This would be similar to what we see around Neptune, where some rings are continuous while others exist as clumpy segments scattered around specific orbital locations. If Chiron has ring arcs instead of complete rings, that changes the physics entirely. Arcs are typically maintained by shepherd moons, small satellites that gravitationally confine material into specific orbital zones. But we haven't detected any moons around Chiron, despite multiple searches using different techniques. Either the shepherds are too small and dark to see, or something else entirely is creating the arc structures. One possibility that's gaining attention is that Chiron's irregular shape is doing the shepherding itself. Computer simulations show that objects with complex non-spherical gravity fields can create zones of orbital stability interspersed with regions of chaos. Particles that wander into the chaotic zones get ejected or crash into the surface. Particles that find the stable zones can survive for extended periods. The mathematics behind this are incredibly complex. Unlike the simple inverse square law gravity of a spherical body, irregular objects create gravitational fields that change constantly as they rotate. Particles experience forces that vary not just with distance, but with orbital phase, rotation angle, and the specific shape of the gravitational landscape they're navigating. Recent dynamical studies have identified something called spin-orbit resonances around Chiron. These are special orbital configurations where particles complete a certain number of orbits, in the same time it takes Chiron to complete a certain number of rotations. The mathematical ratios create zones of enhanced stability, like gravitational sweet spots where material can accumulate and persist. 2 of Chiron's confirmed rings appear to sit right in these resonance zones. That's not a coincidence. If the resonances are actually confining the ring material, then Chiron represents the first known example of a self-shepherding ring system. No external moons required. The object's own complex gravity field acts as both the source of instability that clears most orbits and the source of stability that preserves a few special ones. Testing this idea requires knowing Chiron's exact shape, mass distribution, and rotation state with precision we don't currently have. The object is too far away and too small for direct imaging to resolve surface features. We can estimate its overall dimensions from brightness variations and thermal observations, but the details of its gravitational field remain largely unknown. This is where future spacecraft missions become essential. Only by visiting Chiron directly can we map its shape and internal structure with the accuracy needed to understand how its gravity field works. Such a mission would take years to plan and execute, requiring careful trajectory calculations to reach an object that's constantly moving through the outer solar system. But the scientific payoff would be immense. A spacecraft could image the rings directly, measure their particle sizes and compositions, track their evolution over months or years of close observation. It could map Chiron's surface geology, identify the source regions of different outgassing events, monitor how ring material is created and supplied through active processes. Perhaps most importantly, a dedicated mission could search for those elusive shepherd moonlets. If they exist, they're probably only a few kilometers across, too small and dark to detect from Earth-based telescopes. But a spacecraft with high-resolution cameras could spot them, map their orbits, and determine how they interact with the ring system. The discovery of shepherd moons would solve some mysteries but create others. How did such small objects form around Chiron? Are they fragments broken off during ancient collisions? Captured asteroids that wandered too close? Aggregations of ring material that somehow accumulated enough mass to become gravitationally bound? Each possibility implies different formation mechanisms and evolutionary histories. Or maybe there are no shepherds at all. Maybe Chiron's rings are maintained by processes we haven't thought of yet. Maybe the constant injection of fresh material from outgassing events is enough to maintain structure despite gravitational spreading. Maybe magnetic fields, electrostatic forces, or other non-gravitational effects play a role in organizing the particles. The more we learn about small body physics, the more we realize how many mechanisms we haven't considered. Asteroids and comets aren't just gravitational systems. They're electromagnetic, thermal, chemical, and geological systems all rolled into one. Forces we ignore when studying planets become significant when dealing with objects where surface gravity is measured in centimeters per second squared. Electrostatic charging from solar-wind interactions can levitate dust grains off surfaces. Thermal cycling can create stresses that fracture rocks along crystalline planes. Chemical reactions can alter surface properties in ways that affect how particles stick together. Magnetic fields, though weak, can influence the motion of charged particles over long timescales. All of these effects become more important as objects get smaller and their gravitational dominance decreases. On Earth, electromagnetic forces are negligible compared to gravity for most macroscopic objects. But in the weak gravity environment around a small comet, electromagnetic effects can compete with gravitational ones, creating dynamics that pure gravitational models miss entirely. This is why Chiron is so scientifically valuable. It's operating in a regime where multiple physical processes compete and interact, where no single mechanism dominates completely. By studying how these different forces balance and combine, we gain insights into physics that applies throughout the universe, wherever small bodies congregate and evolve. And the implications extend far beyond our solar system. Every star has debris disks during its formation phase. Every planetary system goes through periods when small bodies migrate and collide and reorganize. If objects like Chiron are common, if ring formation around small bodies is a normal part of planetary evolution, then ring systems might be ubiquitous features of young stellar systems. We're already seeing hints of this in observations of debris disks around other stars. Space telescopes can detect dust clouds and organize structures around distant suns, but the resolution isn't sufficient to determine whether those structures include rings around small bodies. Future telescopes with higher resolution and better sensitivity might reveal that the galaxy is full of ringed asteroids and comets, mini versions of Saturn scattered throughout every planetary system. This would fundamentally change our understanding of how planets form. Instead of thinking about planetary accretion as a purely collisional process, we'd need to consider how ring systems around small bodies contribute to the mixing and transport of material. Ringed objects could act as temporary reservoirs, collecting and organizing debris before releasing it back into the general population through collisions or gravitational interactions. The chemical implications are equally profound. If ringed bodies are common, and if they can maintain their structures over millions of years as they migrate through planetary systems, then they become vehicles for transporting and redistributing volatile materials across vast distances. Water, organic compounds, and other biologically important molecules could be carried from the outer reaches of stellar systems into the inner zones where terrestrial planets form. This connects to one of the biggest questions in astrobiology. How did Earth acquire the water and organic compounds necessary for life? The traditional answer involves bombardment by comets and asteroids during the late heavy bombardment period roughly 4 billion years ago. But if those impactors were carrying ring systems filled with concentrated volatiles, the delivery efficiency could have been much higher than simple collision models suggest. Think about it this way. A comet impact delivers whatever volatile materials are contained within the comet's nucleus. But a ringed comet impact could deliver both the nucleus materials and whatever additional volatiles are contained in the ring system. If rings can concentrate and preserve materials over long periods, they might represent a previously unrecognized mechanism for delivering the ingredients of life to planetary surfaces. Testing these ideas requires understanding how common objects like Chiron really are. So far, we know of only a handful of small bodies with confirmed ring systems: Chariklo, Haumea, Quaoar, and now Chiron. But these discoveries came from targeted observations of specific objects during rare occultation events. We haven't conducted a systematic survey to determine what fraction of small bodies might host rings. Such a survey would require coordinated international effort. Thousands of objects would need to be monitored for occultation opportunities. Prediction algorithms would need to be refined to identify the best candidates for observation. Telescope networks would need to be positioned and synchronized to maximize the chances of capturing useful data. The logistical challenges are immense, but the potential scientific return is even greater. If ring systems are common among small bodies, we're looking at a hidden component of solar system architecture that we've completely overlooked. If they're rare, then objects like Chiron represent extraordinary windows into exotic physical processes that operate under very specific conditions. Either way, we need to know. Because the story of Chiron isn't just about one unusual comet orbiting between Saturn and Uranus. It's about understanding how matter organizes itself throughout the universe, how complexity emerges from simple physical laws, and how the cosmos continues to surprise us with phenomena we never anticipated. The next few years will be crucial. More occultation campaigns are already being planned. Advanced computer simulations are being developed to model multi-engine systems and complex gravitational environments. Space agencies are beginning to consider mission concepts that could visit Chiron or similar objects directly. But perhaps most importantly, Chiron is teaching us to question our assumptions about what's possible in space. For too long, we've relied on simplified models that work well for idealized cases, but break down when confronted with the messy complexity of real, astronomical objects. Chiron is forcing us to embrace that complexity, to develop more sophisticated tools and more nuanced understanding. And as we do, we're discovering that the universe is far stranger, far richer, and far more creative than we ever imagined. The impossible rings around a tiny comet are just the beginning. They're pointing us toward a deeper appreciation of how matter behaves in the cosmic arena, where the rules we learned from Earth-based physics must be expanded and refined to accommodate realities we're only now beginning to perceive. The journey is far from over. In fact, we're just reaching the point where the real discoveries begin. Because what Chiron has shown us about ring formation and small body dynamics is opening doors to questions we never thought to ask about planetary evolution, astrobiology, and the fundamental nature of how worlds come to be. These discoveries aren't happening in isolation. They're part of a broader evolution in how we understand complexity itself. While astronomers grapple with Chiron's rule-breaking physics, researchers in completely different fields are making breakthroughs that illuminate the same fundamental questions about how order emerges from chaos. In materials science laboratories, physicists have achieved something that textbooks said was impossible. They've successfully manipulated quantum geometric effects in magnetic materials at room temperature. For decades, these phenomena were confined to extreme environments, temperatures near absolute zero, magnetic fields powerful enough to levitate frogs, conditions that cost millions to maintain and could only be sustained for brief moments. But in 2025, researchers working with a compound called terbium manganese tin demonstrated that quantum geometry, the mathematical framework describing how electrons organize themselves in materials, could be controlled using modest magnetic fields at everyday temperatures. They observed electrons forming structures that classical physics insisted shouldn't exist, creating responses that could be switched on and off like a quantum toggle switch. The parallel to Chiron is unmistakable. Just as ring particles are organizing themselves in gravitational environments where classical mechanics says they should scatter, electrons in quantum materials are maintaining coherent behaviors in thermal environments where classical physics predicts chaos. Both systems reveal that the boundaries we've drawn between order and disorder, between what's possible and what's forbidden, are far more permeable than our simplified models suggested. This isn't just academic curiosity. These quantum materials breakthroughs are pointing toward technologies we can barely imagine. Sensors that exploit geometric quantum effects could detect magnetic fields with unprecedented precision. Memory devices that store information in quantum geometric states could operate faster and more efficiently than anything currently possible. Computing architectures that harness these effects might solve problems that would take conventional computers millennia to crack. But the deeper significance lies in what these discoveries reveal about the nature of reality itself. Both quantum materials and objects like Chiron are showing us that complexity can emerge through mechanisms we hadn't recognized, that matter has hidden capabilities for self-organization that operate across vastly different scales. At the quantum level, electrons coordinate their behavior through mathematical relationships that transcend simple particle interactions. Around distant comets, dust grains organize themselves through gravitational resonances that create structure from apparent randomness. The mathematics might be different, but the underlying principle is the same. Nature has multiple pathways for building order from chaos, and we're only beginning to map those pathways. This realization is transforming how scientists approach complex systems everywhere. In biology, researchers are discovering that protein folding, the process by which amino acid chains assume their functional three-dimensional shapes, involves quantum mechanical effects that persist at body temperature. Enzymes, the molecular machines that drive biochemical reactions, appear to exploit quantum tunneling and coherence to achieve efficiencies that classical chemistry cannot explain. Even more remarkably, artificial intelligence is now participating in this exploration of complexity. In 2024, an AI system called ESM3 evolved a completely novel fluorescent protein through computational processes that compressed hundreds of millions of years of evolution into a few weeks of calculation. The resulting protein, ESMGFP, had never existed in nature, but functioned perfectly when synthesized in the laboratory. This achievement represents something profound about the relationship between natural and artificial processes. The protein was genuinely evolved, not designed. The AI didn't plan its structure like an engineer drafting blueprints. Instead, it explored the vast space of possible amino acid sequences through iterative testing and selection, allowing functional structures to emerge through algorithmic evolution. The connection to Chiron becomes clear when you consider that both systems involve the exploration of possibility space through physical processes. Around Chiron, countless particle trajectories are tested against the realities of gravitational dynamics and collision physics. Most fail, leading to particles that either crash into the surface or escape into space, but a few succeed, finding stable orbits that allow ring structures to persist and evolve. In computational protein evolution, countless amino acid sequences are tested against the constraints of thermodynamic stability and biological function. Most fail, producing proteins that misfold or lack activity. But a few succeed, creating functional molecules that solve specific biochemical problems through purely evolutionary processes. The mathematics of both systems involves optimization under constraints, the search for solutions that satisfy multiple competing requirements simultaneously. Ring particles must balance gravitational attraction against centrifugal forces while avoiding collisions and navigating complex orbital resonances. Protein sequences must balance structural stability against functional requirements, while satisfying the chemical constraints imposed by amino acid interactions. This convergence isn't coincidental. It reflects something fundamental about how complexity emerges throughout the universe. Whether we're talking about electrons in crystals, particles around comets, or molecules in living cells, the same principles apply. Variation generates diversity, constraints filter possibilities, and selection amplifies successful solutions. But here's where the story takes an unexpected turn. Recent advances in artificial intelligence are revealing that these principles can be accelerated and directed in ways that nature alone cannot achieve. AI systems can explore possibility spaces faster than biological evolution, test more configurations than physical processes, and identify solutions that might never emerge through purely random search. This capability is already being applied to problems throughout science and engineering. AI systems are designing new materials with properties tailored for specific applications. They're optimizing drug molecules for enhanced effectiveness and reduced side effects. They're even generating artistic works and musical compositions that exhibit creativity indistinguishable from human expression. The implications for understanding objects like Chiron are staggering. If we can simulate evolutionary processes computationally, we might be able to model the evolution of ring systems with unprecedented detail and accuracy. Instead of building simplified mathematical models that capture only the most basic physics, we could create comprehensive simulations that include all the competing processes we suspect are operating around Chiron. Such simulations would test thousands of different scenarios, different outgassing patterns, different particle size distributions, different rotation states, different gravitational environments. By running these virtual experiments and comparing the results to observations, we could identify which combinations of processes are most likely to produce the structures we see around Chiron. The computational requirements would be enormous, tracking millions of particles through thousands of orbital periods while accounting for collisions, gravitational perturbations, thermal effects, and electromagnetic forces pushes the boundaries of what even supercomputers can handle. But the same AI techniques that evolved proteins in silico could potentially be adapted to evolve ring systems in computational space. Imagine an AI system that generates thousands of different models for Chiron's internal structure and activity patterns, then test each model against observational data to see which ones best reproduce the ring configurations we've measured. Over many iterations, the system could converge on models that not only explain current observations but predict future behavior with testable accuracy. This approach could reveal insights impossible to obtain through traditional theoretical analysis. It could identify subtle feedback mechanisms between different physical processes, predict optimal conditions for ring formation around small bodies, and perhaps even suggest new observational strategies for detecting similar systems elsewhere. But the most profound implication concerns the nature of discovery itself. For centuries, scientific progress has depended on human insight, creativity, and intuition. Scientists observe phenomena, develop hypotheses, design experiments, and gradually build understanding through accumulated knowledge and inspired leaps of imagination. Now we're entering an era where artificial intelligence can participate directly in this process. AI systems are not just tools for calculation or data analysis. They're becoming collaborators in the scientific enterprise, capable of generating novel hypotheses, identifying patterns humans miss, and exploring theoretical landscapes too complex for purely human navigation. In 2025, researchers unveiled AI Newton, an artificial intelligence system that can derive physical laws from raw data without any prior knowledge of physics. Given measurements of position, velocity, and acceleration, AI Newton rediscovered Newton's laws of motion and gravitation. Fed astronomical data, it identified conservation principles and orbital mechanics. Presented with thermodynamic measurements, it derived the laws governing energy and entropy. This represents a fundamental shift in how scientific laws are discovered. Instead of human physicists spending years developing mathematical frameworks to explain observations, AI systems can identify the underlying patterns and relationships directly from data. They don't just fit equations to measurements, they discover the concepts and principles that make those equations meaningful. The potential applications to Chiron research are immediately obvious. An AI Newton descendant could analyze the entire observational record of Chiron's rings, outgassing activity and brightness variations, then propose new physical laws that govern ring stability around irregular bodies. It might identify relationships between rotation state, internal structure, and ring dynamics that no human physicist has considered. Such AI-derived laws wouldn't replace human understanding, they would accelerate it, providing new frameworks for human scientists to explore and validate. The partnership between human creativity and artificial intelligence could unlock insights that neither could achieve alone. But this convergence of AI and physical discovery raises profound questions about the nature of understanding itself. When an AI system derives a physical law, has it understood something about the universe? Or has it simply identified mathematical patterns in data without comprehending their deeper significance? The question becomes even more complex when we consider that human understanding might itself be a form of information processing, a pattern recognition system operating on biological hardware rather than silicon chips. If consciousness and comprehension are emergent properties of sufficiently complex information processing systems, then the distinction between human and artificial understanding might be less fundamental than we assume. These philosophical implications extend far beyond the study of comets and ring systems. They touch on questions of consciousness, creativity, and what it means to know something about the universe. As AI systems become more sophisticated, as they participate more directly in scientific discovery, we'll be forced to reconsider our assumptions about intelligence, understanding, and the nature of knowledge itself. Meanwhile, back in the cold reaches of our solar system, Chiron continues its ancient dance. Tumbling through space with its impossible rings, venting primordial gases, evolving in real time, completely indifferent to our philosophical struggles with the nature of artificial intelligence and scientific discovery. But perhaps that indifference is itself instructive. Chiron doesn't care about our categories, our models, or our assumptions about what should be possible. It simply exists, following the laws of physics as they actually operate rather than as we think they should operate. In its stubborn refusal to conform to simplified theories, it's teaching us something essential about the relationship between human understanding and cosmic reality. The universe doesn't organize itself for our convenience. It doesn't limit its complexity to what we can easily comprehend or model with our current mathematical tools. It explores the full range of possibilities allowed by physical law, creating structures and processes that challenge our assumptions and expand our sense of what's possible. Chiron represents one small example of this cosmic creativity, but it's an example that's accessible to human observation and analysis. Unlike distant galaxies or exotic quantum states that can only be studied indirectly, Chiron is close enough for detailed investigation, active enough for real-time monitoring, and complex enough to reveal fundamental principles that apply throughout the universe. As we continue studying this remarkable object over the coming decades, we'll undoubtedly discover new surprises that force us to revise our understanding yet again. The ring structure might evolve in unexpected ways. New outgassing mechanisms might be identified. Previously unknown physical processes might be revealed through improved observations and more sophisticated models. Each surprise will be valuable not just for what it teaches us about Chiron specifically, but for what it reveals about the general principles governing complex systems throughout the cosmos. From quantum materials to biological evolution to artificial intelligence, the same fundamental themes keep emerging. Complexity arises through the interplay of variation, selection, and constraint. Order emerges from chaos through processes we're only beginning to understand. And in that emergence, in that constant generation of novelty from the interaction of simple rules and complex environments, we find something that might be the most profound characteristic of the universe itself. It's creative, it's generative, it's constantly exploring new possibilities and bringing new forms of organization into existence. Chiron isn't just an anomaly to be explained away, it's a teacher, showing us that reality is far richer and more surprising than our theories suggest. It's an invitation to think more broadly, to question more deeply, and to embrace the complexity that makes the universe endlessly fascinating. The story isn't ending, it's just beginning. Because every answer Chiron provides raises new questions, every mystery it solves reveals new puzzles, every boundary it breaks opens new territories for exploration. That's what makes it the strangest comet in our solar system, and perhaps the most valuable teacher we could ask for in our quest to understand the cosmos we inhabit. In laboratories around the world, researchers are discovering that the boundary between different states of matter is far more complex than classical physics suggests. Materials can exist in quantum superpositions, maintaining multiple organizational states simultaneously until specific conditions force them to choose one configuration over another. This quantum behavior was thought to be limited to ultra-cold temperatures and isolated systems, but recent breakthroughs have shown that certain materials can maintain quantum coherence even in noisy room-temperature environments. The discovery suggests that the classical world we experience might be more fundamentally quantum than we realized, with quantum effects playing hidden roles in processes we thought we understood completely. The connection to Chiron's ring dynamics becomes apparent when you consider that both systems involve matter existing in states that seem to violate classical expectations. Chiron's rings persist in orbital configurations where Newtonian mechanics predicts they should collapse. Quantum materials maintain coherent electron behaviors in thermal environments, where classical statistical mechanics predicts decoherence. Both phenomena suggest that our understanding of when and how different physical regimes apply is incomplete. The boundaries between classical and quantum behavior, between stable and unstable configurations, between order and chaos, are more nuanced and context-dependent than our simplified models capture. This realization is driving a fundamental shift in how physicists approach complex systems. Instead of trying to force observations into existing theoretical frameworks, researchers are developing new mathematical tools that can handle multiple competing processes operating simultaneously across different scales. The computational challenges are immense. Modeling quantum effects in materials requires tracking the quantum states of billions of electrons, while accounting for thermal fluctuations, electromagnetic interactions, and structural dynamics. Simulating ring formation around irregular bodies like Chiron involves similar complexity, tracking millions of particles through gravitational fields that change as the central body rotates. But the potential rewards justify the effort. These computational approaches could reveal organizing principles that operate across vastly different scales, from quantum materials to planetary rings to biological systems. They might identify universal mechanisms for the emergence of complexity, patterns that repeat throughout the natural world despite involving completely different physical processes. The implications extend beyond pure science into technology and engineering. If we can understand how matter self-organizes under different conditions, we might be able to design systems that exploit these principles to create new forms of functionality, quantum materials that switch between different states on command, ring systems around artificial bodies that sort and concentrate valuable materials from space debris, biological systems that self-assemble into desired configurations for medical or industrial applications. But perhaps the most significant implication concerns our understanding of the universe itself. If complexity emerges through universal principles that operate at every scale, then the cosmos might be fundamentally creative in ways we're only beginning to appreciate. Not just following predetermined laws, but actively exploring possibilities, generating novelty, creating new forms of organization that weren't present before. This perspective transforms how we think about objects like Chiron. Instead of seeing them as anomalies that violate established rules, we can appreciate them as examples of the universe's creative capacity, demonstrations of what becomes possible when physical laws interact in complex environments over long timescales. Chiron has been orbiting the Sun for billions of years, slowly migrating inward from the Kuiper belt through the gravitational influence of the giant planets. During that journey, it has experienced countless environmental changes, different radiation levels, different thermal conditions, different gravitational perturbations. Each change has left its mark on the object's structure and composition, creating the complex system we observe today. The ring formation might be a recent development, triggered by Chiron's migration into the region between Saturn and Uranus, where thermal conditions became just right to activate internal ice transitions. Or it might be an ancient feature that has persisted throughout Chiron's journey, maintained by processes we don't yet understand but that operate reliably over cosmic timescales. Either way, Chiron represents a natural experiment in planetary physics that has been running for longer than complex life has existed on Earth. It's a test of how matter behaves under conditions that can't be replicated in any terrestrial laboratory, a probe of physical processes that operate over timescales that dwarf human civilization. And now, at this moment in cosmic history, we have the technology and theoretical frameworks needed to study this experiment in detail. We can track Chiron's evolution in real time, measure the properties of its ring system with unprecedented precision, and develop models sophisticated enough to capture at least some of the complexity that drives its behavior. We're living through a unique window of opportunity. Chiron is active now, changing on timescales we can observe, revealing its secrets through ongoing processes rather than ancient frozen records. In a few million years, its chaotic orbit will either send it crashing into the Sun or eject it from the solar system entirely. This is our chance to study one of the universe's strangest creations while it's still accessible to human observation. The lesson extends far beyond astronomy. Throughout science, we're encountering systems that challenge our theoretical frameworks, phenomena that exist at the boundaries between different domains, objects that refuse to fit neatly into established categories, quantum materials that behave classically under some conditions and quantumly under others, biological systems that exhibit both random and directed evolution, artificial intelligence systems that display creativity and insight alongside purely computational processing. These boundary-straddling phenomena aren't exceptions to be explained away. They're windows into the deeper principles that govern how complexity emerges throughout the universe. They're teaching us that the neat divisions we've drawn between different fields of science are artifacts of our limited perspective, not fundamental features of reality itself. Chiron sits at the intersection of multiple scientific disciplines. It's simultaneously an object of astronomical observation, a laboratory for planetary physics, a probe of geological processes, and a teacher of orbital dynamics. Its ring system involves gravitational mechanics, electromagnetic effects, thermal processes, and perhaps even quantum mechanical phenomena operating at macroscopic scales. No single theoretical framework can capture all aspects of Chiron's behavior. Understanding this object requires integrating insights from across the physical sciences, developing new mathematical tools that can handle multiple interacting processes, and embracing a level of complexity that challenges our traditional approaches to scientific modelling. But that complexity isn't a bug in the universe's design. It's a feature. It's what makes reality endlessly fascinating, perpetually surprising, and infinitely worthy of study. every time we think we've figured out how something works, nature reveals new layers of complexity that force us to expand our understanding yet again. Chiron is giving us one of those expansion opportunities right now. It's showing us that small bodies in the outer solar system can be far more dynamic and complex than we ever imagined. It's demonstrating that ring formation involves processes we hadn't considered, operating under conditions we thought were impossible. And in doing so, it's preparing us for the discoveries that await as we continue exploring the solar system and beyond. Because if Chiron can surprise us this thoroughly, if an object we've known about for decades can still reveal fundamentally new physics, then imagine what we'll find as we study thousands of other small bodies with similar precision. The universe is full of Chirons, objects that appear ordinary until examined closely enough to reveal their extraordinary nature. Each one is a teacher, a puzzle, a doorway into deeper understanding of how the cosmos works. And each one is waiting for us to develop the tools and perspectives needed to appreciate its lessons. That's what makes this moment in the history of science so exciting. We're not just accumulating more data about known phenomena. We're discovering entirely new categories of behavior, new ways that matter can organize itself, new demonstrations of the universe's creative capacity. Chiron isn't the strangest object in our solar system, because it's uniquely weird. It's the strangest because it's the first one we've studied carefully enough to appreciate just how strange ordinary things can be when examined with sufficient precision and theoretical sophistication. The real question isn't what makes Chiron special. The real question is how many other seemingly ordinary objects are harbouring equally extraordinary secrets, waiting for us to look closely enough to notice. The answer, almost certainly, is most of them. That's the universe we inhabit. Not a clockwork mechanism following predictable rules, but a creative system constantly generating new forms of complexity, new demonstrations of what becomes possible when physical laws interact in rich environments over cosmic timescales. Chiron is our invitation to explore that creativity, to embrace the complexity, and to prepare ourselves for the surprises that await as we continue pushing the boundaries of human knowledge. The journey has only just begun, and the destination is far stranger and more wonderful than we ever dared imagine. So here we are, standing at a crossroads in our understanding of the cosmos, while 3i Atlas captured headlines as it swept through our solar system in 2025. Carrying its exotic chemistry from distant stars, it was Chiron that quietly shattered every rule we thought we knew about how matter behaves in space. This humble resident of our own cosmic neighbourhood, with its impossible rings and real-time evolution, has proven that the strangest mysteries aren't always found among interstellar visitors. Chiron has taught us that complexity emerges everywhere, from quantum materials organising themselves at room temperature to ring particles defying gravitational logic around irregular bodies. It's shown us that the universe operates through principles we're only beginning to understand, where multiple engines can drive impossible structures, where boundaries between order and chaos are far more permeable than our simplified model suggested. As artificial intelligence begins participating directly in scientific discovery, as we develop tools capable of exploring possibility spaces faster than nature alone, we're entering an era where the distinction between natural and artificial creativity becomes increasingly meaningless. What matters isn't the origin of complexity, but its endless capacity to surprise us. The next time you look up at the night sky, remember that somewhere between Saturn and Uranus, a tiny world is tumbling through space with its impossible rings, venting ancient gases, evolving before our eyes. It's a reminder that the universe's strangest secrets aren't hiding in distant galaxies or exotic dimensions. They're right here, waiting for us to look closely enough to see what was always there. And that might just be the most extraordinary discovery of all.